So we're going to start lesson 21. This is all about titrations, and you may not remember back in second semester, but there was a small section, I think chapter 4.5, that mentioned titrations, and we skipped it way back then because they just introduced some brief terminology, which is what we're going to start with today, and then they don't actually cover like any of the calculations until you get all the way to chapter 14. So some of this you may not find in your chapter 14 reading because it's back in chapter 4. And so this is, titrations are all experiment 8 information, which we're supposed to do the week following spring break, but we will now be doing hopefully 2 weeks after spring break when we are all back together on campus. So some important terminology. In a titration, you're going to have a couple of important pieces. But the goal of a titration is usually to quantify how much of an analyte we have in a sample by adding a known amount of a reagent. And we know this because we're going to know the mole to mole ratio. So if we know the amount of moles of this, then we can determine the amount of moles of that and determine its concentration. So there are some important pieces to the titration. You can see there's arrows here. The long skinny glass tube filled with a blue liquid is called a burette. In lab we've used microburettes, the little bitty syringes, but in experiment 8 we're going to use really large burettes that can hold 50 milliliters. So they're normally big like this. The blue liquid is called the titrant. So this is what we know, the known amount. And then the pink at the bottom is called an analyte. This is our unknown. Okay, so those are the important pieces. And we're adding the titrant through the bottom of the burette into the analyte, and that is what a titration is. So equivalence point versus endpoint. What's the difference? So an equivalence point is going to be the point at where neutralization occurs. So the point of the titration where neutralization occurs. So another way of saying this is that hydronium or proton concentration is equal to hydroxide, OH concentration. So up here, the titrant can either be a strong acid, strong base, weak acid, weak base, and the same is true for the analyte, but they're going to be opposites. Either the titrant is an acid and the analyte is a base, or the titrant is a base and the analyte is an acid. It can be done either way. The endpoint, on the other hand, is going to be the point at which there is a sudden color change. And we're going to be more broad and say a sudden change in a physical property of the analyte. Oops, I should spell that correctly. Analyte. And so this could be color, pH, absorbance, value, etc. And so we've done one where we've seen color changes when we did yellow, to blue, pink to colorless. Okay, so those are the examples, and that's what the end point means. So now let's label, and the important thing here is that they're not always the same. Okay, they can be different. So now we're going to have a curve. This is the first problem, and we're going to go through and label each point. So in the titration curve, we should have pH, and then we're going to have volume, and this is usually volume of titrant added. Okay, so the amount of blue that we've added to the pink, if we think about the colors of that previous image. So if you're unsure, like is this an acid or a base, this is usually measuring the pH of the analyte. Okay, so we're measuring the pH of the pink solution as we're adding the blue solution over time. So we can see here that the pH is starting off greater than 7, which means that this is a base. Okay, and so if we remember back, bases are going to accept protons, therefore leaving us with OH, which is where the high pH between 7 and 14 comes from. So the point at where there is approximately 100% base and none of the product, well, that's going to be at the very beginning. So let's go ahead and extend our line, okay? Because that volume here at 0, well, this is where we have only base and none of the product, the conjugate acid. So B says the point at which there is approximately 50% of the base and 50% of the conjugate acid. So this is where we've converted half and half. And that's going to be right here at the inflection point. Okay, right there where, if you remember, inflection is where the slope's going to change, where it starts to go in, and then it's going to all of a sudden switch and go out. Okay, so that's the point at which we have half and half. The last part says where there's approximately 0 of the reactant, and 100% of the conjugate acid. And we're just going to label this C at the end because we see it starts to flatten out. Okay, so there's no more base to react with. All of it is now converted to the conjugate acid. So we have the first 3. D is going to be the buffer region. So this is where we see no change in the pH, even though we're adding something. And so that's going to be this flat area right here. Okay, let me make that a different color. The flat area, okay, where there's no change, even though we're adding our titrant, the pH is staying stable. Okay, so that's going to be the buffer region. Now the equivalence point, where we have half and half, half and half, is going to be the same as B. So this is going to be B and E. Halfway to the equivalence point, if this is the equivalence volume, right here, the amount of volume it takes to get to the equivalence point, well then half of that, which is approximately right here, that's halfway to the equivalence point. So this is VEQ half. Okay, so I just took the volume on the x-axis and divided it in half, and this is halfway to the equivalence point. Excuse me. The last part says the point at which the pH is equal to the pKb of the weak base, and this is always going to be equal to the half of the equivalence point. So they are the same. Okay, so this is where pH is equal to the pKb. All right, so we've labeled our graph. So now problem 2a is identifying what type of titration is occurring. So we have a couple different options. Is it a strong or weak acid or base? Titrate with a strong, weak acid, or base. So there's kind of 4 combinations: strong and strong, weak and weak, strong and weak, weak and strong. And we need to identify that as well as the acid base. So starting off here, I know that this is an acid. So my analyte in this case is acidic. And that means my titrant must be a base. And I know that because my starting pH is between 1 and 7. And so then the pH is going to become basic eventually. Now, when I need to know whether it's strong or weak, I need to look at where the equivalence point is. And in this case, the equivalence point is about 7. So the only time that you have an equivalence point of 7 is when you take a strong acid and a strong base, and it produces a salt and water where the salt is neutral. Okay, so you think back to that lesson 18, I think, where we talked about how we could tell if they were going to be acidic or neutral. All right, so next one. We have starting off a basic. So that means my analyte must be a base, and my titrant cannot be a base. It must be an acid. It's got to be the opposite because it eventually becomes acidic. And again, my pH equivalence point is about 7, making this a strong base, strong acid for the very same reasons. Third one, it's going to start off acidic. So my analyte is an acid. My titrant must be a base because eventually it's going to become basic. And my equivalence point is approximately about 5. So what this would suggest to me is that the acid, the analyte itself is strong, but I'm only titrating it with a weak base, which is why the equivalence point is less than 7 and not higher than 7. All right, last one. So I'm starting off at a basic pH, making this a base, and then I'm titrating it with an acid because it's going to become acidic over time. And my equivalence point is about maybe 5, 4, between 4 and 5. So what this tells me is that I'm starting with a weak base and titrating with a strong acid. If it was a strong base with a weak acid, I would see that the equivalence point would be between 7 and 14. And so because the equivalence point is acidic, that means that what I'm adding is much more strong than whenever I'm starting with my analyte. So what are the key differences that I'm using to identify the types of titrations being performed? One, I'm comparing the starting pH and the ending pH. Okay, helps me to determine what I'm starting with and what I'm adding. I'm looking at the equivalence point to determine does the equivalence point located neutral, acidic, or basic? And those are my 3 features. All right, and so the last one says, what titration curve would you expect with a weak acid titrated with a strong base? Well, let's see, I would expect that my weak acid, it's going to start off here in the acid range, okay? And if it's a strong base, I would expect that my equivalence point is going to be up higher and end up there. Let's see. Let's actually try to make my equivalence point correct. Okay. So it would look something like that. Okay. All right, so let's do some calculations. We're going to have 3 different versions. We're going to have strong and strong, weak and strong, and then weak and weak. Actually, I don't think I'm going to ask you any weak and weak. Yeah, we're just going to do strong and strong, weak and strong calculations. So when we have a strong and strong titration, the nice thing is we know that when a strong acid and a strong base react, it goes to 100% to form the salt and water. Okay, so we're going to use mole to mole ratio to calculate most of this information. So this problem tells me I'm going to take 50 milliliters of this and titrate it with HCl. So this is my analyte. This is my titrant. So I'm going to write the balanced chemical equation. Well, it's KOH plus HCl. It's a double displacement reaction as well as neutralization. So my K and my Cl are come together and my H and OH will come together to form water. It's in a 1-to-1 mole ratio, which makes it nice and easy. So remember, you have to make sure it's not diprotic or triprotic. because it's not going to be 1 to 1. So this says find the pH when no HCl has been added. So I'm only going to concern myself with the KOH. So remember that when we have KOH by itself with water, this is the predominant reaction that is occurring. Okay, it's the only source of hydroxide, therefore it's going to be the main contributor to the POH. So I'm going to take the initial concentration at the molarity that I'm given in the problem, and that gives me a POH of 1.52. But in order to put that in terms of pH, I subtract it from 14, which tells me that the starting pH, just KOH, is 12.48, which makes sense because we're starting with a strong base. So I would expect it to be basic. Now this says calculate the volume of titrant at equilibrium. So what we're looking for is VEQ. Okay. So in this case, I can consider mole-to-mole ratio. So the first thing I need to do is determine how many moles of KOH I have by using the molarity and the volume, which is 50 milliliters, which becomes 0.05 liters. And I'm starting with 0.0015 moles of KOH. Because it's in a 1-to-1 ratio, yes, I could just skip a step, but because it may not always be 1-to-1, I'm going to go ahead and write out the conversion based on the balanced chemical equation here, because it won't always be 1-to-1. And now I need to know where did it go? There we go. The molarity of the HCl to get to volume, because this should be in milliliters or liters. And I'm told that I'm starting with a 0.1 molar solution of HCl. So then my moles of KOH cancel out, my moles of HCl cancel out, leaving me with just volume. And essentially you're going to multiply all the way across, divide by the bottom, and you're going to get that to get to the equivalence point, I'm going to have to add 15 milliliters of HCl. Okay, so it's important to know the equivalence point. It's going to be one of the first things that you do, okay, because at some point the VEQ is going to become important. So this says, what will be the pH after 10 milliliters of HCl is added? Well, if I know the VEQ is 15 milliliters, well, this is before. Okay, so if we think back to the curve, right now I'm starting with a strong base and I'm in this region right here. Okay, so I am before the equivalence point. In order to do that, I need to determine how many moles of HCl I have added based on the volume. So this is what I started with KOH. And at this point, I have 0.1 molar HCl, and I've added approximately 10 milliliters per the prompt. So what this tells me is I've only added 0.001 moles of HCl. All of those moles of HCl are going to react with the KOH because I'm not at the equivalence point yet, meaning I'm still going to have excess base that contributes to the POH, which then I can use to solve for pH. So I would expect that at this point the number of moles of KOH are going to be greater than the moles of titrant I've added, and it is very slightly in excess. but I have a new volume. I started with 50 milliliters of KOH and I've added 10 milliliters of HCl. So my new volume is 60. Okay, so I have the number of moles, and to get molarity so that I can plug it into the negative log of, I'm going to divide by the volume, the new volume. So this is going to give me a molarity of KOH of 0.0083. So it should go down because I have consumed some of my KOH at this point. So now I can solve for the POH. And that comes out to be 2.08. Convert that to pH. And lo and behold, we can see that the pH has changed just a little bit. The pH started off at 12.48 right here when it was just KOH, and now it's at 11.92 after I've added 10 milliliters of HCl. Okay. Now this says, what is the pH at the equivalence point? Well, this is where it's important to have identified it was a strong acid and a strong base, because we said earlier it's going to produce a salt and water, where the salt is neutral. So the pH at the equivalence point would be 7, because it's a strong acid and a strong base. The last part says, what is the pH after 18 milliliters of HCl is added? Well, this is after the equivalence point. So the predominant species at this point is going to be HCl. And all of the HCl that's excess is going to contribute to pH directly. So I'm still going to start off with my initial amount of KOH that I solved for up in part C. But now when I solve for moles of HCl, I'm going to use this volume that's given here to calculate how many moles of HCl I have now. So my volume is going to cancel out, and this is going to leave me with 0.0018 moles of HCl added. But I only had 0.015 moles of KOH available. So I'm going to take the difference between the two. And if you subtracted them opposite and got a negative number, you just cannot have negative numbers. It's just the absolute value. And this leaves me with 0.0003 moles of HCl excess. My new volume is going to be the 18 that I added, the 50 that I started with, giving me a volume of 68 milliliters. So I can divide the number of moles of HCl excess divided by the new volume of the solution, and that gives me a molarity of 0.0044 molar. Now this time, since the HCl is excess, I'm only solving for pH because there's only H plus ions around. All of the OH has reacted with the HCl to form water, and then whatever HCl added that was extra is going to contribute to a pH, which is 2.36. Okay, so that's after the equivalence point. Now this says to draw the expected titration curve. So initially we started off with a pH of about, let's see, I should have highlighted it, 12.5. And then at a volume of 10, it's at 11.92. So when I've added 10, it's going to be approximately 11.92. The equivalence point we determined was 15, so that's where we'd have a pH of 7. And then at a volume of 18 added, the pH went down to 2.36. And we really don't know anything other than that because it doesn't we don't have any other numbers. So now we're going to connect the dots as best as we can. And then we're just going to estimate that last line. Okay? So there you go. Okay, those are probably the easiest problems. Okay, so practice strong, strong. You could do a strong acid as the analyte and a strong base as the titrant, and the calculations are the same. You need to identify the equivalence point, determine if you're before or after the equivalence point, make sure you know the mole to mole ratio, and then you just take the difference. It's like a limiting reactant problem, an excess reactant problem. So similar to what we did last semester. All right, so weak and strong titrations. These you're going to have to devote some time. Okay, there's going to be, it's important, but it's worth it. And there's going to be a whole worksheet, lesson 23 worksheet, which I'll solve individual problems for later and upload the video so you guys can be as prepared for the test as possible. So weak, strong titration. This says consider the titration of 20 milliliters of acetic acid with a certain concentration. So this is weak and it gives you a Ka, and then we're going to use a strong base as the titrant. So what's the equation? Well, the equation when they're reacting is the acetic acid and the OH. It's going to do the sodium and the acetate ion come together to form sodium acetate, and then of course it creates water. Okay, so you have the Na and the acetate, the proton and the OH coming together. Now the initial pH, when only acetic acid is present, so this is before the titration begins, no NaOH. It's going to look just like our problems we've done before, where we have our weak acid with water. Because it's an acid, it means it's going to give up its proton to the water, forming hydronium, right? Because that's going to be acidic starting off with. And so it's just going to be a normal ice table, because we know that there's equilibrium present. It is not like a strong acid, strong base problem. We're starting off with a certain molarity. Water doesn't count, none of the acetate, none of the H3O plus. Therefore, the reaction is going to shift to the right to consume reactants and produce products. These are my I plus C equal E. I need to test my rule about the Ka. So Ka 1.8 times 10 to the negative fifth times 1,000. It's going to leave me with, which is less than the starting amount of 0.105, meaning I can get rid of this minus x, which simplifies my life significantly. So now I'm going to take the products over the reactants, just like we've been doing all along for several lessons now, in fact several chapters. And I'm going to solve for x, which x is going to come out to be 0.001357 molar. And I want to know the pH. So if I know what x is equal to, I know what hydronium is equal to, and I can plug that in to the pH is equal to the negative log . And I should get a pH of less than 7, which I do, which is 2.86. So that's my initial pH of acetic acid before I've added any sodium hydroxide. So for part C, it says it wants to know the amount of NaOH needed to reach the equivalence point. So I'm solving for the volume of NaOH. I'm going to do it just like I did the previous problem, by starting off with how much of my acetic acid, how many moles I have. And I started off with 20 milliliters with a certain, I'm going to abbreviate that acetic acid, with a certain molarity, 0.105. which means to get to the equivalence point, I have to consume 0.0021 moles of acetic acid. Now, fortunately for us, according to the balanced chemical equation, this is a 1-to-1 ratio. 1 mole of acetic acid is going to react with 1 mole of NaOH. And then to get the volume, I need to use the molarity that I'm given in the problem, which is 0.125. And that will get me to the volume of NaOH needed, which is 0.0168 or 16.8 milliliters. Typically in titrations we use milliliters, but the molarities are always in moles per liter, so it's kind of a sloppy conversion that we make, but we usually will convert this to milliliters to discuss that. Okay, so that's my equivalence volume right here. Now I'm going to use that, the VEQ, to determine if I'm before or after equilibrium, or at equilibrium, because sometimes that can happen too. So when I am before equilibrium, I'm going to treat it like a buffer. Okay, so in this case, I'm going to be at a volume of 10 milliliters, which is before VEQ. Okay, because my volume isn't at equilibrium, or my titration isn't at equilibrium until 16.8 milliliters. So what's happening now is this reaction that we saw before, the one that we started off with, because I have started titrating. Okay, so it's a buffer. It's the acetic acid, which is weak, and the conjugate base, which is the salt of my weak acid. Oh, this should say weak acid. So it's a buffer problem. Okay, which means Henderson-Hasselbalch. But the problem is I need to know what my AHA values are. So to know what my AHA values are, I need to solve for the amount of what the moles I have at this point. So I have this molarity of acetic acid, and this is my starting volume of acetic acid, which means just like before, I have 0.0021 moles of acetic acid. And I've added, up to this point, 10 milliliters of my NaOH, which is a certain concentration of 0.125. So this is going to tell me that at this point I've added 0.00125 moles of NaOH, which makes sense that I have more acetic acid than NaOH at this point because I'm not at the equivalence point. But what I do know is that some of the NaOH has consumed some of the acetic acid. So to determine how much is being consumed, I'm going to take the difference between the two, which tells me at this point I only have 0.00085 moles of acetic acid left. My volumes I've added together, I've taken 20 milliliters and 10 milliliters and added them together, which means my new total volume is 30 milliliters or 0.03 liters, giving me a molarity of 0.028 molar of my acetic acid, which in this case of my AHA is going to be my HA. And so what about my A, my A? Well, this is all of my A minus because all of the Na is going to directly contribute to my sodium acetate, so I can make a direct conversion because they are in a 1-to-1 ratio with each other, the sodium hydroxide and the sodium acetate, and divide that by my new volume to get my molarity of my A. Okay, so now I have my AHA, I know my pKa, which is the 1.85 or 1.8 times 10 to the negative fifth plus the log of my ha. And when you solve for everything, you end up getting a pH of 4.92. Okay, so to solve for it, you have to determine how many moles have been added at this point, how many moles I had, how many moles I've added, take the difference to reflect what's been consumed of the acetic acid, and divide it by its new volume to solve for the fact that it's been diluted to a new molarity, and then take the number of moles of base that have been added and convert that to molarity using the new volume to solve for my conjugate base, my A minus concentration. All right. So to find the pH at the equivalence point, I know the volume because I've been given that volume. So at this case, what is going to dominate is the CH3COO minus will dominate. Okay, so this is my weak base that's going to dominate. Okay, if I was titrating with a acid, then it would be the opposite. Okay, so this is going to dominate the reaction that's occurring at this point because it's the predominant species is now the opposite. Okay, so at this point, if we think about this reaction, I have shifted so far to the right that now the conjugate base becomes the predominant species, and then it's now going to be in a whole new equilibrium where the conjugate base becomes the predominant species and it's in equilibrium with the acetic acid, and what starts taking over is the POH component. So in order to solve for the the pH, I'm going to need the concentration of the A minus, okay, which is this right here. And I know that in order to solve for that, I need to know how many moles of NaOH I have added, and I need to divide it by the total volume because all of the sodium hydroxide that I've added is going to directly produce the NaCH3CO minus, the sodium acetate. So I can use the moles of the acetic acid because I know that it's a 1-to-1 ratio. So if I have 0.0021 moles of acetic acid, well, that's the number of moles of NaOH I'm going to have to add to neutralize all of the acetic acid. I started off with 20 milliliters of the acetic acid, and I've added 16.8 milliliters of NaOH, so that's my new volume, and I get a new molarity of 0.057 of my A. So if I'm going to set up an ice table where A minus plus water equals my HA plus OH, I'm going to start off with this amount of A minus, none of the HA, none of the OH. Reaction is going to shift to the right. Okay. Now my Kb value, because this is basic, I know I need a Kb, where Ka is equal to the 1.8 times 10 to the negative fifth, giving me a Kb value of 5.56 times 10 to the negative 10th. So for sure, if I multiply this by 1,000, it's still going to be much smaller than my 0.057. So in this case, because this is smaller, I get to get rid of that minus x, which makes my life a lot easier. So now I'm going to take Kb products over reactants. Set that equal to my Kb value and solve for X, which is 5.63 times 10 to the negative 6 molarity. Now this is equal to the OH minus concentration, so when I plug it into the negative log of, I'm technically solving for the POH. The POH, when I solve for that, is 5.25. So to solve for the pH, I'm going to take that number and minus it from 14, which gives me a pH, which is basic, of 8.75, which would make sense because I'm taking a weak acid and titrating with a strong base. So VEQ would be expected to be a basic pH based on all those curves we've done before. Okay, so the key here is that because this is the dominant species, we need Kb, okay, for our ice table. All right, almost there. So now we're going to find the pH after 20 milliliters of NaOH is added. This is after the equivalence point. So at this point, it's an excess base problem. So we're going to treat it very similar to what we did at the end of the strong, which is at this point I've added 20 milliliters of NaOH. And I only started with 0.0021 moles of acetic acid. Okay, so it's an excess by a very small amount. I started with 20, got those backwards. I started with 20 milliliters. I've added 20 milliliters, which gives me a new volume of 40. So I'm going to divide that by the new volume, which gives me a molarity of 0.01 molar. Because it's an excess base, I'm still solving for POH. So it switches at this point. Take the negative log of that concentration, and we get that POH is equal to 2.00. To solve for pH, I'm going to subtract that from 14, which gives me a pH of 12. And then the last thing we're going to do is graph it. So to start off with, my pH was about let's make sure I get this right, 2.86. And my equivalence volume, well, let's do the next one. After about 10 milliliters, the pH was about 4.92, so that's kind of halfway between here. I had a pH of about volume of about 16.8, which is nearly 17. The pH at that point was 8.75. So these are really rough estimates. And then at 20 milliliters, the very last one, the pH was all the way up to 12. Okay, so rough estimates, where VEQ is right here. Okay, and so then this last thing here says be sure to practice weak base, strong acid titrations as well. I would really just recommend practicing all of the stuff in lesson 22 and lesson 23. And then if you're still confused, do your sapling homework. Try to do it without your notes. The hardest part's predicting which calculation you need to do, but if you solve for the VEQ, you're at least getting somewhere. You'll know if you're before or after the equivalence point, which helps you get started. Okay, so I'm not sure how long this video ended up because I didn't record, but lesson 22 and 23, what I'm going to do is record individual videos for like question 1 so that you can practice them and watch them one at a time. Okay.